Okay, so let's summarize all the results we know about the shortest path algorithm. It's kind of a zoo, so it would be useful to kind of go through them carefully. Okay, so if we don't have any negative cycles, we can just use the extra. That takes n log n time plus n, right? Again, n is the number of vertices, and m is the number of edges. Okay, so this is what the extra gives us. If there are negative edges, things get much worse. We have to use Bellman-Ford. The running time becomes nm, right? Which is by order of magnitude worse, right? It's essentially from linear time algorithm, we get into quadratic time algorithm. So this is for single source algorithm. For all pairs shortest paths, if there are no negative edges, we can just use the extra n times and get a pretty decent running time. N square log n plus nm. Okay. We can also apply Bellman-Ford n times, but then we get a running time which is in the worst case n to the fourth. Then the algorithm we've seen Floyd-Warshall, and Floyd-Warshall work in n2 cubed. Now it turns out, by the way, I'm telling you this is for general information. This is in no way something that we covered in the course, but there is a very clever algorithm that first runs Bellman-Ford and then run the extra n times. It uses something called potential function and so on. And then you do the all pair shortest path in this time, nm plus n square log n, which is better than Floyd-Warshall. This is, of course, just for your general knowledge, right? The basic idea is somehow that Bellman-Ford can be used to kind of precondition the graph. And again, this is too complicated to go into, although it's kind of interesting to see that one can be improved over what we currently have. And then, as I said, there is Floyd-Warshall. For unweighted case, one can start using a matrix multiplication algorithm. Why matrix multiplication has any connection to shortest path is completely not obvious, but think about it somehow that it's similar in concept to Floyd-Warshall. Somehow this operation of picking a middle vertex in the path is similar somehow to multiplying matrices at some philosophical level. Anyway, this is again something I'm just mentioning for general knowledge. This is not something we'd see. This is just know that it exists, that there is some bizarre connection between shortest path in the graph and matrix multiplication. Okay, so this is the result we have, and a few results that just for your information. And as I said, this algorithm that is Bellman-Ford and the extra n time is kind of the best one can hope for at some level. Okay, this is it.